A warm greetings to everyone. Let me start by asking you a question. Do you want to buy a product and want to know about the talks on it? Or you want to go for a movie and you are unaware about the reviews and still worried about it? Forget your problems. You are at the right place. We are Team Profit Titans and here to introducing our idea and solution named as Emonexa, an emotional tool for the next generation, which performs the sentimental analysis of the social media presence. It has potential to empower both individuals and businesses. Our product is termed to be a multi-model containing more than two standalone models, which is especially designed to produce a high precision analysis from the social media data. After a thorough information gathering, we came to a conclusion that the current sentiment analysis tools are only limited with text-based inputs and treats all the users with the same priority. But our main goal is to produce a multi-model which accepts three types of inputs, which are text, speech, and image, which will be explained in detail in the upcoming minutes. We are even enhancing the depth of our tool by introducing categorization with the factors like age, expertise, and popularity. Our tool also analyzes more than three emotions. As you can see in the top right corner, we have made a diagram which explains the whole process in short, starting from the data fetching from the social medias by Emonexa bot, and then processing the data in the multi-model, and finally producing a categorized data which can be analyzed and visualized to produce a high precision recommendation for the users. Below we have our technology stack in which we are using React.js for the front end and Firebase for the back end. We are using TensorFlow, PyTorch, DeepFace, Google APIs for the multi-models. And next, when we move on, we have our analysis and research about the present multi-model and sentiment analysis tools. You can pause and go through it once. And this is our flowcharts based on the uh, product, and this is based on the categorization part. And the next flowchart is based on the multi-model part, which is in detail about the image, speech, and text. And then finally we have our use cases, which are nothing but it can be used for product and brand feedback analysis, educational feedback, healthcare patient feedback, market research, and many more. And we also have few dependencies for our projects, which are nothing but the API availability, social media data access, which is the important one, model bias, feedback loop, scalability, and many more. And we will be explaining and going through detail about each model of the multi-model in the upcoming minutes.
The code that you're seeing right now is text-based sentiment analysis model, which makes use of the long short-term memory model, which is a recurrent neural network for NLP tasks. We generally use RNN-based models since they are designed to deal with sequential data. Loading the necessary libraries. This section imports the necessary Python libraries and modules. It includes numerical and plotting libraries like NumPy and Matplotlib, deep learning libraries like TensorFlow and Keras, text processing tools like Tokenizer and patch sequences from Keras, NLTK for natural language processing, Pandas for data handling, and scikit-learn for label encoding and dataset splitting. And then we load the dataset into as a data frame. And we are loading and pre-processing of the dataset. We load a dataset using Pandas library. The dataset consists of two columns, sentence and sentiment. The text data in the sentence column is extracted and stored in the sentence list, while sentiment label in the sentiment column are stored in the sentiment list. This part encodes the sentiment labels into numerical values using scikit-learn's label encoder. It converts labels like positive and negative into corresponding integers, making them suitable for model training. Tokenization converts sentences into sequence of numerical tokens, and padding ensures that all sequences have the same length. The code uses Keras tokenizer to tokenize the text and pad sequences to pad sequence to a maximum length of 100. And then we split the dataset. This line splits the dataset into training and testing sets using scikit-learn's train test split function. It allocates 80% of the data for training and 20% for testing with a specified random state. And then we create a LSTM model. This section defines the architecture of the LSTM model using Keras. It includes an embedding layer for word representation, an LSTM layer for sequential processing, and a dense layer with softmax activation for multi-class classification, and is compiled with a sparse categorical cross-entropy loss function, which is suitable for multi-class classification problems. Then training the model. Here the model is trained using the training data. The training process includes 5 epochs, which you can adjust, and a batch size of 64 samples. It also uses a validation split of 20% of the training data to monitor the model's performance. Then the test loss and accuracy are printed and calculated and displayed as performance metrics. And then we visualize the training history. Matplotlib is used to create a plot for the training loss and validation loss over the epochs. This helps visualize how well the model is learning from the training data. Then finally we have predictions. The code prepares new text data for sentiment prediction. A sample sentence is provided for prediction. The label mapping dictionary is used to map numerical predictions back to sentiment labels and decodes the numerical predictions into sentiment labels using the label mapping dictionary. Finally, the code prints the original sentences along with their predicted sentiment labels. As you can see, the sentences, this, and the sentiment that is provided by the model is positive. This is the actual value from the dataset where we can confirm that the sentence is this and the sentiment is positive. So the model works fine, and we will more fine tune it in such a way that it can produce much more accurate sentiment for any kind of text-based analysis. So far this is for the model.
The purpose of the application is to enable users to perform speech recognition in real time through the microphone. It serves as a simple and user-friendly tool for converting spoken language into text. The main features and purposes of the application are as follows. The primary function of the application is to convert spoken language into text. Users can speak into their microphone and the application attempts to recognize and transcribe the speech in written words. Users can select the language in which they are speaking. The application supports a wide range of languages, allowing users to specify the language of their speech, which aids in more accurate recognition. Real-time interaction. The application provides a real-time interaction, meaning that users can initiate their speech recognition process by clicking a button. The application listens to the user's voice as they speak and displays the recognized text as soon as the speech is complete. We've used Python's speech recognition library for the speech-to-text conversion part, along with the Streamlit for the user interface and the web application. So, the futuristic plans are, we're planning to include an option in which the user uploads an MP3 file consisting of varying audio, and the application tries to auto-recognize the language of the MP3 file and converts it into text. Now let's check a sample. I'll give the input languages English, this is again English. This is a good day. Yes, as you can see, the application has successfully translated the words which I said in my speech. Thank you. Below is the implementation of speech emotion recognition using LSTM. LSTM stands for Long Short Term Memory Model. It's a type of recurrent neural network widely used for emotion analysis from audio data. It is the preferred choice over other architectures like CNN for several reasons. Sequential data handling. Audio data, especially speech, is inherently sequential. Emotions are often conveyed through the timing, prosody, and intonation over time. The next is temporal prompting. LSTMs can model time series data effectively by maintaining internal memory states. This allows them to remember and utilize information from distant time steps, crucial for recognizing emotional cues that span various moments within an utterance. Feature extraction. LSTMs can extract relevant features from audio data over time, including pitch, energy, and rhythm, which are essential for emotion recognition. They learn to represent these features effectively by processing audio sequences, enabling richer feature extraction. Next, emotion analysis to plots. In addition to the modeling capabilities, LSTMs are often used to generate and analyze plots for different emotions. These plots, such as waveforms and spectrograms, provide visual representations of audio signals that help identify emotional patterns. For instance, angry emotions may exhibit sharp spikes in the waveform and intense high-frequency components in the spectrograms. Stateful memory. LSTMs have a memory cell that retains information over time, allowing them to capture nuances in emotional expression that build up or change gradually within an audio clip. Waveplot and spectrogram characteristics for different emotions. The TESS Toronto dataset has around 7 different emotions, namely angry, disgust, fear, happy, neutral, sad, and surprise. First, we'll analyze the emotion called as fear. Fearful speech may involve quivering or trembling in the voice, leading to small, rapid oscillations in wave plots. Spectrograms may exhibit fluctuations across various high frequencies, including low and high frequency components. Next, angry. The waveplot may exhibit sharp, intense spikes indicating abrupt changes in the speech. The spectrogram often shows high-frequency components representing intense and energetic speech. Disgust. Waveplots may display irregularities, possibly short, erratic bursts, and spectrograms can have variations in both low and high frequencies. Neutral. Waveplots for neutrality tend to be steady with consistent amplitude, resulting in relatively flat waveforms. Spectrograms show a consistent distribution of frequencies without significant peaks. Sadness. Sadness is often expressed with slower, gradual variations in amplitude, leading to smoother waveplots. Spectrograms may show a concentration of lower frequencies and less pronounced high-frequency content. Surprised. Waveplots for surprise may have a sudden and sharp changes in speech, resulting in abrupt spikes. Spectrograms often exhibit bursts of high-frequency content and irregularities in frequency distribution. Last but not the least, happy. Waveform for happiness typically appears smoother and more rhythmic, resulting in regular wave plots. Spectrograms show a balanced distribution of frequencies, reflecting a lively tone. The LSTM model has around 5 different layers. The first is the LSTM layer, next it has 3 dense layers and a dropout of 0.2 respectively. The optimizer that we have used is the Adam optimizer, and the model has an accuracy of around 99.9.
So in this code, we'll be exploring a Python script that showcases the real-time face recognition using OpenCV, Pygames, and the DeepFace libraries. So we'll be beginning our code by importing some of the necessary libraries like OpenCV, which is a very essential tool for the computer visions and image processing, and the Pygames, which is a versatile library for creating the interactive applications. Also NumPy, TensorFlow, uh, and also we'll import some of the DeepFace libraries which specializes in deep learning based facial analysis. And we here first will be initializing our camera by using the OpenCV with the video capture. So this sets up the system to capture the video from the default camera, and then we'll be initializing the Pygame with the Pygame init, which is helps in getting ready to create the graphical user interface components. And next we'll be defining our colors, font, and the backgrounds for the user interface. Here comes the how we set up and display our background image by using the image load. This image will be served as a backdrop for our application, and we by using the display set mode we'll make sure that the window size matches the background image dimension, and optionally we can rotate and scale the background image as needed. And here is a main loop which is the heart of our code. So the core of our code resides in this main loop, and it is responsible for continuously updating and displaying the video feed. And also we use a while loop that runs as long as the running variable is set to true. Within this loop, we update the screen with the background image and captures a frame from the camera using the OpenCV, and also perform the real-time face recognition using the DeepFace libraries. Next is the face recognition results. That is, when a face is detected, these lines handles the processing of the display, the recognized results. We extract the emotion of the recognized person and coordinates of their face. Then we draw a green rectangle around the detected face and display the name nearby. This provides a visual indication of the recognized face. And next few lines of the code are about converting the processed image video frame into a format that the Pygame can display. We transfer the frame into a Pygame image and enhance it by adding a semi-transparent white rectangle around it. And next is for centered display. To make sure that the image we are doing is to be centered, we use these few lines of the code which ensure the image is displayed at the calculated position. And last is the user interaction, which is very crucial for any graphical application. These lines check for the user events such as clicking the closing button on the Pygame window. And finally, we clean up and quit by using the release and the capture. So these lines of code is about training the data, and we have set a test set which is sad image. So this when we run this, we can see that it is displaying the sad. This is a sample example. So let us see how this code actually works and how it detects by running the code. So this is how our camera will be detecting the face and analyzing based on the training data set, and will be displaying the contents like happy, anger, sad, and surprise. So this is all about.
Sentimental analysis. So, what's different between a normal text sentiment analysis and Twitter text sentimental analysis is Twitter tweets consists of many different kinds of text like emojis and HTTP links, and even in Twitter we can tag other users in Twitter. So this is done in many social media platforms, but in Twitter, what we can do is we can hurt the sentiments of other people, we can troll someone, we can scold someone, etc. But most of these tweets are made in an indirect way. This is allowed in Twitter, but not in other social media platforms like Instagram. So, because it's done it in an indirect way, it's very hard to predict the nature of the tweet. Like, is it negative, neutral, or positive? So, Twitter sentiment analysis is surely a challenge. So, to overcome this challenge, we already used a model like Hugging Face, which is trained with over 6 lakh Twitter tweets. So, what we do is, if there is any tag to the user, we'll convert the tag to iterate user variable, which would be easier for the model to predict, as the tag will not add any value to the model. And any HTTP link, you see, any like the HTTP link will not consist any sentiment, like it's not neither negative nor neutral nor positive, so it's just converted to a HTTP word. So here we are going to take three tweets from a very well-known data set. The first tweet is a positive tweet according to the data set. The second tweet is neutral tweet, and the third tweet is a negative tweet according to the data set. So we'll just check this on the model. So let's see how our model performs. So this is a positive tweet according to the data set. So let's check the value. So the model predicts with high probability that this tweet is a positive tweet. So the model is working fine for this tweet. Let's take another example. So this is a neutral tweet according to the dataset. Let's see how our model performs. So here you can see, comparatively, it's predicting that the tweet is a neutral tweet, but the probability values are not so different. But still, the model is able to correctly predict that this tweet is a neutral tweet. So this is it for this.
And then we are importing preprocessor.py and helper.py. These store the separate function files which are being importing from here. And then we have the usual matplotlib and seaborn for all those analysis path. And then here this part of the code is the one where you'll be getting the uploaded files as the form of WhatsApp chat exported files without media, so that can be taken directly from WhatsApp. And then here we have the top statistics where we have total messages, total words, media shared, number of links shared, and everything. And we have monthly timeline, daily timeline, activity map, then most busy day, most busy month, weekly activity, most busy users, and etc. So this we have a preprocessor where we'll be using regular expressions, and we'll be finding out we'll be extracting date, time, and the messages separately from the WhatsApp exported file. And then here we have our we have our data frame where we'll be having users, their messages, the date, year, month, date, name, hour, minutes, and etc. And these are the helper functions which we use for word clouds and those data analysis parts like those, bar charts and etc. So for that we are using this help of .py function. So here this is our streamlit UI. So now I'm browsing file. So I'm uploading a WhatsApp group message exported file. So once it's uploaded, it will be giving us with an option like show analysis. So it's an overall analysis. So there you can see. So once we click show analysis, it gets. Let's wait for some time. So here we have the statistic being uploaded. So here we have total messages, total words, media shared, links shared, and this is the monthly timeline. And along with we have daily timeline, then activity max. It shows the most busiest day is Saturday, and then the most busiest month was October. Then weekly activity maps. So it shows like at what time mostly they are being used. And 3 to 4, none of us will be available. So it shows fully dark coins, and then there's busy users gives like the percentage was who chats a lot. So here it's like Vishwa Ramasubramanian is the one who chats a lot can generate. The other feature which we have is this was an overall analysis. We can have user based analysis. So for example, if we click like Vishwa Ramasubramanian show analysis, it runs and then so now we have the top statistics again. So here is the total messages given by him and total words, media shared, and his monthly timeline, his daily timeline, then which day he was most busy, like chatting. So it's again it's here Sunday, and then the busiest month is the same as the one for overall October.
So now finally we are at the end of our video where we have our React.js front end and our Firebase backend. So in this uh, we have to create a login form for the user where he can fill all his details, and we'll be extracting those details in the from the front end, and we'll be providing it in the backend. So for that we have app.js here where we have linked all the pages through React router. One is login page, sign up page, and the other is detail page. So the login page has fields like email, password, and if the user already has an account, then he can directly log in. Else he has to go for the sign up page. And in the sign up page, the user has to enter all his email ID, name, and which will be authenticated with the Firebase in the backend, and then he can go with his login. And after signing up, the user has to go go with providing all his details, and for that we are using React state hooks where all the details will be stored in these variables, and then finally we will be storing it in the backend. So the state hook mainly acts as a dynamic state changing property. So all these details will be stored in variables like location, demographic, age, gender, and then we will be sending it into the backend Firebase using the fetch database command, and all those will be stored in the database. So let me show you the. So this is our uh, first we have a login page, and if the user already has a account, then he can directly go in with the login. Else he has to sign up from here. So for example, I will give my name. now after signing up, the user has to provide all his details like enter your full name. So I have filled three text boxes here, and if the user has this uh, Twitter, Instagram, Snapchat, then those text boxes will be visible because earlier they were in hidden. And after submitting, you will be getting alert that the data has been saved. And when we go to the Firebase backend, we can see that the data which we provided will be available here. Ganesh, Tamil, and music. So this is all about our front end and back end Firebase, and thank you.